Hi, I'm Reto Buzano and I'm talking to you from this beautiful city in northern Italy, from Torino. And today I'm going to talk about non-compact self-shrinkers for mean curvature flow with arbitrary genus. This is joint work with Huy Nguyen, who is currently at Queen Mary University of London, and a former postdoc of Huy and mine, Mario Schulz, who is currently a postdoc at the University of Münster. Okay, and in this talk we will do the following things. So the goals of the talk are to first study a little bit what is known about these self-shrinkers. So here we will focus on a two-dimensional case, and we will see what are self-shrinkers for mean curvature flow, what is their significance in singularity analysis of the mean curvature flow, and also the characterization of these as minimal surfaces in Gaussian space. And we will see a little bit about the known examples so far, and then we prove theorem 1. So theorem 1 is the existence result for non-compact self-shrinkers with arbitrary genus, and we will then also study the limit of these new objects that we find as the genus tends to infinity, and that's theorem 2. And theorem 2 will also say a little bit more about the number of ends of the objects that we find in theorem 1. So these are closely connected theorems. And together these theorems partially resolve a problem that was posed by Tom Illman. Okay, so in the first part, in the first video, I will explain to you all these things, and then in the second part of my talk, I will give short sketches of the proofs of these two theorems, and then I will finish with a few open problems, conjectures, and numerical results. Okay, let's dig right in. So, mean curvature flow and self-shrinkers. So what is a mean curvature flow? A mean curvature flow is the flow of a generally submanifold, but here just a hypersurface, or in fact, if we're in dimension 2, just a surface, a two-dimensional surface in three-dimensional space, and we evolve every point in the direction of its mean curvature. Or in fact, we also can have some tangential motion. The important thing is that the normal motion of every point is in the direction of the mean curvature vector. The mean curvature vector is the same thing as the scalar mean curvature times the normal vector. And the important thing is that while the mean curvature might depend on your choice of normalization, your choice of normal, if you change the normal, the unit normal, to minus the unit normal, then also the mean curvature changes sign. So the mean curvature vector is completely independent of all these choices. Okay, and now this mean curvature flow, this is the gradient flow of the area functional, and in that regard, that means it will decrease area and try to evolve the flow also to something nicer and more regular. Okay. What happens in mean curvature flow is that singularities typically form in finite time. In fact, if you start from a closed surface or compact surface, then actually you must necessarily have a singularity forming in finite time. This can be seen as follows. So take your object, let's say this bit inside here is our original surface, and every point moves in the direction of its mean curvature. And then we just take a large sphere that encloses this surface, and then because the mean curvature flow is a parabolic flow, so it satisfies parabolic equations satisfy some kind of maximum or comparison principle, which geometrically translates into this avoidance principle. That means that if this sphere around and the interior surface, they don't touch initially, then they can never touch along the flow. So we can evolve both with mean curvature flow. What happens to a sphere under mean curvature flow? We just discussed that the mean curvature vector is pointing inside. That means the sphere shrinks and it actually disappears in a point in finite time. So whatever has been enclosed must also disappear, or at least form some singularity before that. Okay? And so these singularities, they are modeled on self-similarly shrinking solutions of the mean curvature flow. That was first shown by Huysken, who invented this monotonicity formula, and he needed a so-called type 1 assumption, so some assumption on how the curvature behaves along the mean curvature flow. And then this was generalized by Illmanen and White, who proved that actually if you're in dimension 2 and you encounter any singularity, then you can always rescale, take these blow-up limits, and see a self-similar solution, just that the convergence might be extremely bad. So it's only in the sense of varifold convergence. And non-compact self-shrinkers, they model local singularities. So let's look at two examples. So the first is a flow where the entire thing just shrinks to a point, so it becomes more and more convex, more and more round along the flow, and then it disappears in a global singularity, so everything disappears in this one point. And if we rescale shortly before that happens, we see an object that looks almost like the round 2 sphere. And then the second object, we have this dumbbell-shaped object that has a thin neck. And then because the neck has a large curvature, we might have a principal curvature in this direction that is negative, and then we have a principal curvature from this cross-section circle that is very positive. So the mean curvature in total will point inwards, and this neck will actually shrink and pinch off. So this is a so-called neck pinch singularity. And what happens here is if you rescale shortly before this singularity happens, you again see a self-similar solution. This time it's the two-dimensional cylinder. So it's a one circle times r. Okay, and this rescaling, of course, will, depending on what factors you use to rescale the sphere and the cylinder, might have different sizes, but if you rescale them to the right size, then you get what is called a self-shrinker. So let's study these self-shrinkers a bit more carefully. Okay, so a self-shrinker, as I have just explained, can actually be seen as a fixed object that would just evolve self-similarly under the flow. So that's our interpretation here. So it's not a flow, it's not a mean curvature flow that evolves self-similarly, but it's just one object, sigma, so that the mean curvature flow actually does nothing else than scale our sigma. Or in other words, if we scale sigma by multiplying with square root of minus t, then we get a mean curvature flow. Okay, and now this mean curvature flow, this has a time, the time of existence goes all the way back to minus infinity. So that tells us, because this is a parabolic flow, there has been an infinite amount of time to smooth and regularize the object. So we expect that these objects are very nice and very regular. Okay. And another characterization of self-shrinkers is via this formula, that the mean curvature is given by 1/2 times the position vector times the normal vector nu. And a third characterization, which we will use quite often in this talk, is that it's a critical point for this Gaussian area functional. So the Gaussian area functional, just like the normal area functional, you integrate with respect to the two-dimensional Hausdorff measure. So this H2 is the two-dimensional Hausdorff measure. You integrate over your surface sigma, but now you integrate with a weight, and this weight is e to the minus 1/4 x squared. And then the factor in front of the integral, so the 1/4 pi, this is just a normalization factor. And we will see in a minute why we have this normalization factor. Okay, the last characterization for self-shrinkers is, of course, if you know you have a critical point for some kind of area functional, then you have a minimal surface in some special space. Here it's the weighted Euclidean space or Gaussian space, where the weight is the same as in the Gaussian area. So it's e to the minus 1/4 x squared. And this is a conformal deformation of Euclidean space. And it's a space that has some nice properties. So in particular, some of the minimal surface theory still applies to this space, but it also has some bad properties. It is incomplete, and it has curvatures going to minus infinity as you approach spatial infinity. Okay, so let's now look a little bit at what are some known self-shrinkers. Okay, we have already seen two before, and here they are again, and the third one as well, which is the plane. Okay, so self-shrinkers with genus 0, they have been completely classified by Simon Brännle, who showed that they can be one of these three. So it's either a flat plane through the origin, or a sphere of radius 2 centered at the origin, or a cylinder of radius square root of 2 centered at the origin. Okay, so in particular you might think that the plane doesn't shrink or doesn't evolve on the mean curvature flow. Of course, it's just a minimal surface, so it doesn't do anything, but you actually could simply rescale it and you don't notice any difference. So in that sense, it's also a self-shrinker for the mean curvature flow. Okay. And now this Gaussian area is actually normalized in such a way that the plane has Gaussian area 1. Okay, because it's a little exercise from analysis 1 that if you integrate e to the minus 1/4 x squared, you get 4 pi. And so this factor 1/4 pi allows us to have f of the plane equal to 1. Now, what is instead f of the sphere and of the cylinder, the Gaussian area of the sphere and of the cylinder? So here in this plot, you see what happens if you evolve the radius of a cylinder. So the red curve shows that the Gaussian area of a sphere of radius r is given by r squared e to the minus 1/4 r squared. And this has a maximum in r equals 2, and that maximum is equal to 4/e. Okay, so this is again a little calculation from analysis 1. And then the blue curve is the Gaussian area of a cylinder, which is square root of pi times r e to the minus 1/4 r squared. And this has also a maximum, and this is at square root of 2, and the value there is square root of 2 pi over e. Okay, now what is important for us is that this maximum, the blue one, is actually slightly higher than the red one. So the Gaussian area of a cylinder is about 1.52, and the Gaussian area of a two-sphere is about 1.47, so it's lower. Okay, the precise values are, of course, not very important for us, but what is actually important is that there's a little gap between the two, and there's a strict inequality. Okay, good. Okay, so what are other known examples? So you can ask what happens if we go to higher genus. So there's an example known with genus 1, and that has been found by Angenen. It's so-called Angenen torus. And so just because You might wonder what the cross-section of this is. So this is kind of an egg-shaped cross-section, and due to this rotational symmetry of the Angen torus, you can actually find this, so the equation for a self-shrinker reduces to an ODE, and you can solve this via a shooting method. Okay. Then the next object that I want to discuss has been found by Nguyen and Capoleas, Collini and Möller independently, and this has been constructed via a desingularization of two self-shrinkers of genus 0, so the plane and the sphere. So imagine you have the sphere and the plane, they intersect at an equator, and then you glue in some kind of shirk surface at this intersection, and the picture here is with genus 11. That's a numerical simulation that we have done, and this way they showed that you can find new self-shrinkers. But their method, as I just said, it's a gluing method where you glue in this shirk surface. This only works for large genus. Nobody really knows how large a genus is. It's just a result that says if the genus is sufficiently large, then these error terms that you pick up with this gluing construction, they're small enough to be able to use some inverse function theorem argument. Okay, so another example, again due to Möller, is the desingularization of the Angen torus and the sphere. Okay, so the picture here above is a simulation with genus 48. So this works again for large genus, and the genus is even in this case. Okay, and again it's not clear what the lowest possible genus is for which this works. So the numerics work down to about genus 12, and then the numerics seem to break down, but it's unclear whether this is just an artifact of our numerics or whether they really don't exist for low genus. Something completely different has been proposed by Chop. So he conjectured that there are these objects that you can obtain by some doubling construction. So imagine you have, let's take twice the sphere, and then let's make one of them just a tiny bit smaller, and then and one a tiny bit larger, and then in between you glue in some kind of catenoidal necks, and then this might look like a self-shrinker. Now, if you try to do this numerically for a small number of necks, you actually find that the self-shrinkers should look like these pictures. And there has been a variational approach to finding these by Ketover for tetrahedral, octahedral, or isocohedral symmetry. So these are genus 3, 5, 7, 11, and 19. And unfortunately, because this is a variational approach, it's not clear whether one actually really finds the objects that are depicted here. So it could be that this construction actually creates additional ends, and if the objects stay compact, then they should look like the ones depicted here, but it's unclear whether one actually finds a compact object in this construction. Okay, and then another general doubling construction has been done by Capoleas, McGrath, but again, this only works for large genus. Okay, so we see in particular, so these are, I think, all or almost all the existence results that are so far known. And in particular, we don't have a genus 2. self-shrinker, and then there's some other gaps, so probably genus 4 and 6, but it's not clear from what genus onwards these other results where we said high genus are actually working. So there might be some gaps. Okay, so this brings us to Ilmanen's problem. And Ilmanen, in his famous lecture notes on mean curvature flow, he conjectured that actually there should be a non-compact self-shrinker with arbitrary genus. And he put this, he called these M-punctured saddles, because these objects look a little bit saddle-like, they have this saddle structure. And he put this problem, says, proof that this M-punctured saddle actually exists for any number of punctures. Okay? And our theorems that I want to present here are actually partially resolving this problem. And so our first result, theorem 1, says that for every genus G, so every natural number in particular, starting at 1 and including 2, which so far nobody has found a self-shrinker of genus 2, there exists a complete embedded non-compact self-shrinker phi G with this genus, so with genus G. Okay, and this in addition is invariant under the action of the dihedral group dG plus 1, so that's the symmetry group of the object. Okay. Now let me say a little bit about the symmetry group. So dG plus 1 is the subgroup of isometries generated by rotations of angle 180 degrees around horizontal axis, and this horizontal axis will then be contained in our self-shrinker. So here we have a picture. We have these horizontal axes that are contained in our object, and if we have a rotation by 180 degrees around one of these axes, then we get the same object. Okay, and then of course the dihedral group, the full group, also contains other objects. For example, if you do a rotation by 180 degrees around this axis, and then you do another rotation by 180 degrees around the next axis, then you actually just get a rotation around the vertical axis. So you also have these vertical rotations as symmetries. Okay, good. So now, by construction, what we will see when I sketch the proof, these objects that we find, they have at least one asymptotically conical end. Or this can actually already be seen from the fact that these axes are all contained in a self-shrinker. So you must have one end that contains all these axes. So this is going to be a asymptotically conical end. And we generally expect that these objects only have one asymptotically conical end. But again, because we construct our objects by some global variational methods, it's currently not possible to actually exclude the possibility that these objects have more than one end. Okay? By theorem of Lu-Wang, self-shrinkers actually, if they have finite genus, they can only have either conical or cylindrical ends. Okay? And Ilmanen conjectured that actually the only way that a self-shrinker can have a cylindrical end is if it's actually isometric to the cylinder. So it is the cylinder. So every other self-shrinker should only have asymptotically conical ends. But even if that conjecture is true of Ilmanen, then there's no way we can currently rule out that the self-shrinkers we obtain have additional conical ends. So that would only mean that there's no cylindrical ends. Okay, so in the second theorem, we study what happens if we let the genus go to infinity. So in that case, our self-shrinkers converge, and I will say in a second how this convergence works. They converge to the intersection of a horizontal plane and a self-shrinking sphere, so a sphere of radius 2. Okay, so in particular that means that for large genus, these objects already look roughly like the plane and the sphere intersected and desingularized, and therefore they have exactly one asymptotically conical end. Okay, so it's not possible that for large genus they have more than one end. Only for small genus that could theoretically happen. We don't expect this, and numerics show that this shouldn't happen, but this is not about numerics, this is about proper mathematical proofs. Okay, and this convergence, so this is again convergence in the sense of varifolds, but it is smooth away from this intersecting circle of radius 2. Okay, so these are our results, and in the next part we want to see how we prove theorem 1 and theorem 2.